Yeah, so question 11. Saturated potassium nitrate, is the molar mass of potassium nitrate, is it like 71? Can somebody Google that for me? 101? Okay. It was something one. So at 40 degrees Celsius, right, we're going to go over to that chart. At 40 degrees, we go up to what, like 60 grams in 100? Oh, unfortunately, I found my calculator. So yeah, we go to 40 degrees, right? We go up to where we cross potassium nitrate. And so we can hold about 60 grams in that solution, right? We add it to the solution by adding it, right? You're adding something, so the volume changes. It's not a 1-to-1, right? Because of solvation. So we added 60 grams. That doesn't add 60 milliliters to the volume. That only adds 25 because of how it goes into solution. I apologize, this doesn't show up as well on this screen for some reason. So we've got 60 grams in for molarity, right? Molarity is moles per liter of solution, right? That's different than molality, where we were looking at kilograms of just the solvent. So we've got to turn grams into moles, and then we can find our molarity. So we've got 60 grams of potassium nitrate, and we know, right, for 1 mole, we have to have 101 grams. That's the molar mass. So we've got 60 divided by 101, right? We get like 0.594 moles. And we have that in 125 milliliters, which is 0.125 liters. So to find molarity, right, moles per liter, so moles over 1.25 liters, and hopefully that's an answer somewhere there. All right, I get 4.75 molar. All right, saved, yeah. So choice D, right, 4.75 molar would be the concentration of potassium nitrate in this solution. Any questions on that one? All right, we'll do question 6. If anyone else wants to line up the next question. All right, we make a solution of antifreeze. Antifreeze, we do that by dissolving 182 grams of ethylene glycol in 525 grams of water. What is the freezing point of this solution, given the freezing point constant of water is 1.86 degrees Celsius per mole now, right? So our change in freezing point equals negative I Kf molality. So we need to know our Van Hoff factor. I give you the freezing point constant, and we have to find our molality. So what is our Van Hoff factor for ethylene glycol? Yeah, 1, right? It's a molecular compound. It's non-metal, non-metal, non-metal. It goes into solution, but it goes into solution as one thing. Right, degrees Celsius per mole. And then to find molality, right? Molality is moles per kilogram of solvent. So 182 grams of ethylene glycol. And we need the molar mass, right? So 1 mole, let's see, 24 plus 6 plus 32, it's about 62. Okay, yeah. 62 grams per 1 mole. All right, so 182 divided by 62, we have, 2.935 moles in solution. And molality, right, is moles over kilogram of solvent. So I've got 2.935 moles, and I have that in 525 grams, which is 0.525 kilograms. And I made it easy and just said that's how much water we have, right? So we could just take that, convert that to kilograms. So divide that by 0.525. All right, we get a molality of, so divide that by 0.525, 5.59 molal. Right, now we can find our change in freezing point, right? Delta TF equals -1 times 1.86 degrees Celsius per molal times 5.59 molal. Multiply all those together, and hopefully we have an answer that's there. All right, times 1.86. And yeah, I get a minus 10.4 degrees Celsius. That's my change. Our solution is water, so yeah, my freezing point would be minus 10.4 degrees Celsius for that. So definitely have to know how to figure out the Van Hoff factor for an ionic compound, for a molecular compound, right? Always one for a molecular compound. We had to find moles, so we could find molality, and then, yeah, just the change in freezing point calculation, right? Put that all together, multiply across to get our change in freezing point is 10.4 degrees. So we're going to freeze. This would have a freezing point of minus 10.4 degrees below 0. Any questions on 6? Yeah. Yeah, so the Van Hoff factor accounts for how many things do we have in solution. And like ethylene glycol, or right, like glucose, right, C6H12O6, they go into solution. They go into solution as one thing, right? So their Van Hoff factor is 1. Right? Whereas something like sodium chloride goes into solution and it forms a sodium ion, which is different than a chloride ion. So it forms 2 separate things. So its Van Hoff factor would be 2. We did like calcium chloride is another example, right? That ionizes and gives you calcium 2+, 2 chlorides, right? That would be a Van Hoff factor of 3, because I go from 1 calcium chloride, right? 1 solid calcium chloride to now 3 separate things in solution, right? 1 calcium and 2 separate chlorides. So for an ionic compound, we need to break down, right? What does this ionize into? How many ions are there? Literally any molecular compound, if it goes into solution, the Van Hoff factor should be 1, because you only get 1 thing in solution. But yeah, good question, good thing to review. Yeah, methanol, right? CH3OH, because that alcohol, right? There's nothing that's ionizing off of that, right? It's don't really have space to, right? CH3OH. Right? It's a covalent bond. These are all covalent bonds. So methanol is going to go into solution, and it's going to go into solution as methanol. There's nothing to ionize. There's nothing it's going to lose as an ion. It depends on the polyatomic, right? Like aluminum nitrate could be 4, right? So it just depends on. Yeah, so right, like these two examples were ionic compounds, but yeah, like a polyatomic, like sodium carbonate, for example, that's going to ionize and give us 2 sodiums. And it doesn't matter that that's a polyatomic ion because that's going to break up into just carbonate. So sodium carbonate, for example, would have a Van Hoff factor of 3, right? Each sodium and then the carbonate. But it would depend, right? I could think of polyatomics like potassium nitrate that we started with. That would be 2. Magnesium nitrate would be 3. Aluminum, nitrate would be 4. Yeah. So it just depends. Any other questions on this one? Correct, right? For boiling point elevation, right, we would be, what temperature are we at above our normal boiling point? The normal boiling point for water would be 100, so we would add that result because we're just calculating not what the boiling point is, but we would calculate, right, the change in boiling point. So we find the change, initial boiling point's 100 degrees, so we'd have to add that to it to say, what is my final boiling point, right? Because the change in boiling point equals final minus initial. So we find this, we know our initial, so to rearrange that, right, to rearrange this equation, we would just add this across. And our rearranged equation would be my final boiling point equals my change in boiling point plus, right, my initial boiling point.